These are types of reactions found in Chapter 11, Section 2 of your book. So we're going to talk about 5 main types of reactions, but that's not an exhaustive list. So just like there are more intermolecular forces than just the 3 we learned, there are reactions that don't fit neatly into these 5 types. There are reactions that span one or more than one of these types, and then there are different types of reactions altogether. So just again to review, and I know I've said this, I think this is the 3rd time I've said it in notes, a chemical reaction is a process where you have one or more substances that are converted into new substances with different physical and chemical properties. So it could be different color, could be different density, could be different odor, could be different state of matter, all sorts of different properties, but it's a new substance. It's not the same substance. And that happens because the bonds that occur in your existing substances are broken, the atoms all rearrange, and new bonds are formed. And so you still have the exact same elements as you had before, and we talked about the importance of balancing the equation for conservation of mass. But now all of those atoms are rearranged, so you have completely different substances that may or may not bear any resemblance. They may or may not have anything to do with the initial substances that they were before. And the reason substances undergo chemical reactions is to gain stability, to become more stable. And this has to do with how reactive different substances are. And as we talked about, again, in balancing equations, not all things are equally reactive, right? I can pour vinegar on baking soda, and I think a lot of us are familiar with this reaction. It bubbles up, it gets all fizzy. I can pour lemon juice on, I don't know, for some reason a piece of toast jumped into my head and the toast gets soggy, but there's no real reaction. That's simply lemon juice on toast. Those two things don't react together. You know, we talked about when I pick up a pen, I don't want my hand to react with the pen. I want those, the chemicals making up my hand and making up the pen to stay separate, not break bonds with one another. So that's very important. So the 5 types of reactions that are really the 5, I would say, main types are synthesis reactions. Your book calls them combination reactions, although I've really not heard that before outside of your book, although it kind of makes sense. Decomposition reactions, single displacement, also called single replacement reactions, double displacement, also called double replacement reactions, and combustion reactions. And as I said before, not every reaction fits neatly into one of these. Some are very clear. Some you kind of look at it and you go, I don't know, that sort of seems a little like a decomposition reaction and a single displacement or something like that. And so that's okay that not everything fits neatly into one of these. And then there are some reactions that take place over several steps. So several of these types may be involved in the overall reaction. And then there are just some reactions that don't really fit into any of these. When we're writing our equations, we have symbols that I haven't introduced you to. And I'm going to show you these in this PowerPoint. So that has to do with the state of matter of the reactants and the products. So we put them in parentheses after the compound or molecule. And so S stands for solid, L stands for liquid. And when we write that, like in handwriting on our papers, we generally do a script or a cursive lowercase l, just so we don't confuse it for a 1 or a capital letter I. G is for gas, and these are all lowercase. And then AQ is not a state of matter necessarily. It's more a physical state. I don't know what you would call it. But it's aqueous, and that means the substance is dissolved in water. So, for example, Salt water, you could say, is aqueous salt. The salt is dissolved in water. That's different from liquid salt, in which you would heat salt up to its melting point, and then you would have a liquid salt. So aqueous salt, salt water, you can have at room temperature. Liquid salt, I want to say salt's melting point isn't until like 800 degrees Celsius, so very, very high, lots and lots of energy. So don't confuse liquid with aqueous. There are certain reasons why you would want to make something aqueous. Water itself is very non-reactive, so in making something aqueous, you still get the properties of that substance without having the solid form of that substance. So if you need something where the ions are not connected, usually aqueous substances are ionic, although they don't have to be. So you could have, if you need the ions to not be connected in that crystal lattice, you would want to make it aqueous, and it's still going to behave like, it's still going to have properties like the solid form, but it'll have some reaction properties that are a little different. So let's look at a synthesis reaction. A synthesis, or a combination reaction, is two or more reactants come together to form a single product. So that's also, you can think they combine. That's why your book calls it a combination reaction. So it's like A plus B yields AB. Pretty straightforward. Here are two examples of synthesis reactions. So 2 sodium plus 2 chlorine gas, plus 1 chlorine gas yields 2 units of solid NaCl. And so here you can see we've got the states of matter that I was talking about. So we have solid sodium with gaseous chlorine, and that yields solid sodium chloride. Don't think that because it's solid and the sodium was solid that this has more properties of the sodium than the chlorine. It just happens that sodium chloride is a solid at room temperature. Here's another one, 4 irons plus, and again, sodium and iron are both metals. Most metals are solids at room temperature. Most gases are gaseous at room temperature. And these, when we're talking about solid and gas and solid, we're talking about under standard temperature and pressure. So 3 oxygen gas molecules, and that gives us 2 units of iron 3 oxide, which is solid at room temperature. A decomposition reaction is pretty much the opposite of a synthesis reaction. So it's a reaction in which a single compound is broken down into 2 or more smaller compounds or elements. So it is the reverse. It's AB decomposes, right? To decompose means to break down. So decomposes into A plus B. So a good example of that is the water example we had in balancing equations, where when you run an electric current through liquid water, if you have 2 moles of liquid water, you get 2 moles of hydrogen gas and 1 mole of oxygen gas. And of course, that 2 moles to 1 mole ratio is why H2O is H2O, 2 moles to 1 mole. And so that's a decomposition reaction. Single displacement reactions. In a single displacement reaction, and I'm noticing now in these notes that we've capitalized displacement and reaction, those are not proper names, or proper nouns. So if you're writing them in a paragraph or in a sentence, you would not capitalize the displacement, or if you said this reaction was a single displacement reaction, those would not be capitalized. Here it's kind of like a title, so that's why we've capitalized them. An uncombined element, or lone element, all alone, displaces, so kicks out, an element that is part of a compound to form a new compound. So it looks kind of like this. A plus BX yields AX plus B. So the A has replaced the B, and the B gets kicked out and is all alone. And I'm going to talk a little bit about these properties, but a lot of times people will use like a high school dance analogy. So they'll say B and X come to the dance together, and A shows up, and X ditches B and ends up dancing the night away with A. And so we'll talk later about why X might do that. It's not the high school reason because X isn't very loyal and saw something better. Well, it is that X saw something better, but it's that A is somehow more reactive than B, and so has kicked B out. So there's actually a chemical reason, but you can think of more reactive metals as more desirable. So, and that X is very fickle and is not loyal at all to B. So the second something more desirable shows up, X ditches B and goes with A. So BX and AX are generally ionic compounds, meaning that B would be positive, A would be positive, and X would be negative, which explains why A replaces B instead of replacing X. Because if A replaced X, you'd have two positives, and those are going to repel. Those aren't going to form an ionic compound. So that's why it's the A replacing the B. A and B then are generally metals. Not in every circumstance, but certainly in ionic compounds they are. The key word here, of course, is generally. In ionic compounds, those would be metals, and X then would be a nonmetal. That's not true of all single displacement reactions. And then here are two single displacement reactions. In each case, it's a metal reacting with copper sulfate, and magnesium kicks the copper out in this case, and the poor copper ends up dancing alone. And here the iron kicks the copper out, and again, the poor copper ends up dancing alone. So poor copper, not very desirable, and sadly the sulfate is not very loyal. Then we have double displacement reactions. Double displacement is atoms from two different compounds replace each other. So one way you can spot a double displacement reaction, and you'll notice here we haven't capitalized, is that you have two or more compounds as reactants and two or more different compounds as products with the same four elements on both sides. I can't really think of a time that you would have the or more. I'm going to kind of cross that out there. I don't like that in there. And so here we have AX plus BY yields AY plus BX, where, again, the A has displaced the B, so Y here is not very loyal to B, but the B is just as happy to go over and kind of hook up with X over here. And so again, if you consider that A and B are going to be positive, and X and Y are going to be negative, that explains why, for example, the B isn't displacing the X, or that A isn't displacing the Y, because you know a positive isn't going to bond with a positive. Those repel. Similar charges repel. And here's a good example of that. So we have 2HCl, and that's aqueous, so dissolved in water. HCl is hydrochloric acid, plus calcium hydroxide, which is also aqueous, and that gives us calcium chloride. So the calcium is essentially replacing the hydrogen, and the hydrogen replaces the calcium. What's interesting is here you have to know something about charges. That goes back to, and you did with single replacement as well, but that goes back to that activity where we were saying, okay, if this has this charge and this has this charge, then what would the compound made with some of this and some of that be? So here you need to know, okay, calcium is 2 plus, chlorine's 1 minus, so that's going to be CaCl2. And then the hydrogen with the hydroxide is going to actually be covalent. That's going to be an H2O. And to balance it, we'll have 2 molecules of that. So you end up with calcium chloride, which is aqueous, and water, which is liquid. And this is actually an acid-base reaction, so we can also call it a neutralization reaction. We'll study acids and bases. They'll probably be one of our last units of the year. But a good way to notice acids, many acids, not all, is that a lot of acids will start with a hydrogen, and a lot of bases will have a hydroxide group. And so then an acid and a base will neutralize one another. And then we get combustion reactions. These are reactions that occur with burning and produce energy. So a campfire is a great example of combustion. It produces light, produces heat, it lots of energy, some sound. And in this type of reaction, an element or compound, often a hydrocarbon, so a compound with hydrogen and carbon, but not always a hydrocarbon, it doesn't have to be, reacts with oxygen gas, O2, and it does have to be oxygen gas. So two ways you can identify a combustion reaction are two of the products must be carbon dioxide gas and liquid water. And so if you think about your car has a combustion engine, and unless, of course, you drive an electric car, most of our cars are combustion engines. They run on octane, which is a hydrocarbon with 8 carbons. And that's what like your octane rating is at the gas pump when it says, do you want 87 or 92 or so. That's the purity of octane in that gas. And then once the reaction drives your car, you end up with carbon dioxide and water, both of which are greenhouse gases, which is why driving cars is such a big deal, because that's the primary product of a combustion reaction. And then oxygen must be a reactant. So both of these have to happen in order to have a combustion reaction. You must have carbon dioxide and water as your products and oxygen gas as a reactant. And so an example then would be, here's propane. So those of you who have propane tanks at home, maybe running a grill, or I know some people have those like fancy outdoor fire pit thingies hooked up to a propane tank. So this is propane gas plus oxygen gas. Often we get that just from the air. And of course, a lot of you have done that just little experiment where you're burning a candle and you put a glass over it and you notice that eventually the candle burns itself out because it's used up all the oxygen. If you never did that back in 3rd grade to see that, yes, in fact, you need oxygen, you might want to give it a try. It's kind of fun. And then that yields our carbon dioxide gas and our liquid water, exactly what we want. So that's a combustion reaction. As I said, it doesn't have to be a hydrocarbon. Propane, of course, is. Your book lists a couple that aren't hydrocarbons, but that is, it's often a hydrocarbon. So feel free to add any questions you have to the YouTube comments or ask in class. Have a good night.